Hello mathematicians, thank you for joining me again today as we continue looking at the function x times x minus 2 cubed. What we've done so far is we found the intervals of increasing, the intervals of decreasing, the local extrema and critical points. We've also found intervals of concavity and the inflection points. And what we want to do is we want to combine that with a little bit more information in order to get a nice sketch of the graph f of x equals x times x minus 2 cubed. So now as we want to graph this, what we want to do is we want to pay attention to everything that's interesting. So before we get into graphing, let's make a list of things that's interesting. And so if I were looking at a graph, what things would catch my eye? Well, a couple of things that might catch my eye are, the first thing I should look at is, what is the domain of the function? Is it defined for all x? Are there some points where it's not defined, that I can't have values? Those are the types of things I want to look at. I might also look at, along with that, are there any vertical asymptotes or holes? Again, those are points that would not be in the domain. So if I have any vertical asymptotes or holes, I want to make sure to make point of that. Along with vertical asymptotes, I'd also want to look at horizontal asymptotes. Now another thing that might catch my eye are intercepts, either x or y. And so what I want to do is I want to find what's the domain, are there any asymptotes, are there any holes, and are there any intercepts, and so I can keep track of that. Now there's more I'm going to want to find out, and the next thing I want to say is, well, the types of things that catch my eye are the highest points and lowest points or extrema, and if it's increasing or decreasing. So I might want to know, is my function increasing, decreasing, and where? Where are my extrema? And so I'm going to have to find those and write those down. Furthermore, I want to know, how curved is it? Is it straight? Is it curved up? Is it curved down? And so what I want to know is concavity, and along with that, any inflection points. So now if I can get all of these things out and plot these correctly, I can get a very nice sketch of the graph. Now, if we look at the first ones we came up with, the domain and the asymptotes, the holes and the intercepts, this is all information we find directly from the function. And that is, we want to know the domain is, well, what doesn't make sense to plug in here? What is the horizontal asymptote is what happens to this as x goes towards infinity. Or the intercepts are, where is the 0, or what is y when x is 0. And so if I look at this quickly, I say that, remember that this is a polynomial, so the domain is all real numbers. So that already means that we don't have any vertical asymptotes and we don't have any holes. And if we look at this as x goes towards infinity, we get a huge number times a huge number cubed is a huge number. So we're going to go off towards infinity, so we won't have a number, so we actually won't have any horizontal asymptotes. So what we're going to have here is that we really just need to focus on what are the intercepts for this function when we're looking at the original function. And so when we're looking at intercepts, we just want to know, okay, if x is 0, what's y? And if y is 0, what's x? And so in this case, let's let x be 0. Then f of 0 is equal to 0 times 0 minus 2 cubed is 0. And so we have the y-intercept is at 0, 0. For the x-intercepts, we're going to let y be 0. And so we'll let 0 equal x times x minus 2 cubed. Remember that a product is 0 if one of the terms is 0. So either x is 0 or x minus 2 cubed is 0. So that means x is 0 or x is 2. And so what we'll have is x-intercepts at 0 and 2. And notice we actually already had this x-intercept as the y-intercept, but now we also have the point 2, 0 on my graph. And so when I'm graphing this, I'm going to want to label the point 0, 0 and the point 2, 0 as points of interest because they were intercepts of the function. Alright, so now for the next information we wanted was, where is it increasing, where is it decreasing, what are the intervals of concavity, what are the critical points, where are the inflection points. Notice that I've actually just written that information down, or condensed it so that we have it. The reason why I was able to do that is for the last two videos, that's what we've been doing. We looked at where was it increasing and decreasing, what were the critical points, what were the intervals of concavity, and what were the inflection points. And so I've taken that work that we've already done and I've combined that together. And if you'd like to look back over that to see how that's done, please see those videos. The nice thing is that when we're doing this, we really want to make this up one step at a time. So that's what I've done, is I've done this work first so that we can go through and now do the full graph. Because we have all that information, what we want to do now is we want to combine it together to get a shape of a graph. So what that means is, and what I'm going to do is I'm going to pay attention to my function and what shape it is by using these number lines. And what I'm going to do is I'm going to make a new number line. So if there's a point on either one of these, I'm going to put them up here. So because 1/2 is on the first derivative number line, I'm going to put 1/2 on the function number line. Because 1 is on the second derivative, I'm going to put 1. And because 2 is on both, I'm going to put it on there as well. Now the reason why I'm doing that is I'm partitioning my number line into places where I have the same shape. That is, it's either always increasing or decreasing, concave up or concave down. So it's always going to look the same on that interval. So if I look at the interval -infinity to 1/2, what I notice is that my function is decreasing concave up. So what I want to think about is, what does a decreasing concave up function look like? And so I'm just going to draw a concave up function. So there's concave up. It looks like a bowl pointing up. I have some cereal in there. If you guys read the posts, you'll notice that I like my Cinnamon Toast Crunch. I put it in there and I get to eat it, and I'm very happy. All right, which half is decreasing though? Is notice that this side is going down, this side is going up. So the left-hand side is decreasing. So if I want a decreasing concave up function, it's going to be bowl shape up, but it's going to be decreasing. So on this interval, what we're going to get is a picture that looks like this. And so we know the shape has to look like that on the entire interval because it's always decreasing concave up. If we continue with that and look at 1/2 to 1, what we have is, well, now we're increasing in concave up. So if I look at my bowl shape up, notice again, I still get to eat my Cinnamon Toast Crunch, but now I'm increasing, so I'm going to be on the right-hand side. So what I'm going to get is a shape that looks like this. Now, from 1 to 2, what I'm going to get is increasing concave down. And so here's concave down. And so notice I let Arthur eat some of my cereal, and he flipped it over, and now my Cinnamon Toast Crunch is all over the table. And I'm very sad about that, because now I don't get to eat it, and I have to clean it up. But besides that, what I do have is that I know my function is going to look like this. And I know I'm going to be increasing. So notice we start by going up and then we go down. So the increasing is the left portion. So if we have increasing concave up, my shape is going to look like that. Now to finish it up, now I am increasing in concave up. So if I go back to concave up, remember increasing was the right-hand side. So I'm going to draw that shape in there. So what I've done is I've combined the information I know about the derivative and the second derivative to get a nice shape of the graph. All right, now that I've got my shape, what I've done is I brought this to the bottom so I have that as a reference. And so I'm going to need some points to use here. And what I'm going to do is I'm going to connect the dots with these shapes. So before I can connect the dots, I have to draw some dots. So I'm going to draw the points of interest that I had. I had an intercept at 2, 0, and 0, 0. I'm going to put a point here and a point here because that was my x-intercepts and my y-intercept. And now I'm going to put in the point 1/2 negative 27 over 16. So here's 1/2 negative 27 over 16 is approximately there. Not quite -2, but more than -1. And remember, we are curve sketching, so it doesn't have to be exact, but we do want to be as close as we can. Now we also had a critical point at 2, 0, but because I've already drawn the point 2, 0 up there, I don't need to do that again. Now I have an inflection point at 1, -1, so I'm going to put the inflection point in there. And I also have an inflection point at 2, 0, but I've already drawn that in. So now what I have is I have 4 points on my graph that are points of interest. They're either critical points, inflection points, or intercepts, things that I want to pay attention to. Now, as we do this, what I want to do is say, okay, well, I need to connect those dots, but I need to use these shapes. So that is from -infinity to 1/2, I need to be concave up decreasing. And so what I'm going to get is something that looks like that. And then from 1/2 to 1, I'm going to be concave up increasing. So So I'm going to look like that. We'll try to make that smooth if we can, but the idea is concave up decreasing, followed by concave up increasing. So now we've connected those dots with those corresponding shapes. Then we can move on and say, okay, we want to go from 1 to 2. Again, we want to make this fairly smooth, but we want to be concave down increasing. So we're going to get something that looks like that. And now from 2 on, we're going to be concave up increasing. So my function is going to look like that. And so we've connected the dots using the shapes that we had, or we found from using the first and second derivatives. Because of that, we were able to get a really nice sketch of the curve. That is, we pointed out all the things of interest. We have the intercepts, we have the critical points, we have the inflection points. And so each of those are drawn in there nicely so that we can focus on the things that are important. Whereas if we had used a calculator, the window would probably not be this window. It would be bigger and it'd be hard to tell exactly where these things are. So it's nice that we can see the details that we're interested in as opposed to just a function graphed on a calculator. And so using these techniques will help us not only do things by hand, but also get better pictures when we're doing things using technology. Thank you for joining me today. I hope you enjoyed it and I hope you learned something along the way. Make sure to subscribe to the channel and like the video.